Friends, I am reviewing the entire course, and we just discussed Ellingham diagrams and explained why the free energy plots, free energies of formation plots for oxides go this way and the slope is negative for CO. In case you wonder why the slope suddenly changes for these lines, it has something to do with a phase change, something solidifies or volatilizes. This has been discussed, so I will not discuss that again. Now, regarding the various steps in pyrometallurgy, we can consider roasting, smelting, etc. There has been, I have discussed a lot of things. I have said there can be so many kinds of roasting reactions, where we talk about converting sulfides to oxides or sulfates or lower oxides, and all these there have been many examples of this. There are also free energy diagrams for metal sulfides. Then I have discussed the predominance area diagrams that show which phases will be stable under different conditions of PSO2 and log PO2. Starting with a sulfide, we can make the sulfate, we can make the oxide, we can make a lower sulfide, we can make the metal, all depending on the phase stabilities. And I have also indicated how we can draw these diagrams by taking into account different reactions. This is the hearth roaster, which is commonly used for roasting, where the feed goes through one hearth to another, and these rotate, and because of rotation some hearths are stationary. On this there is a rotating device, and they throw them from one to the other, and they are all sloped. Later it was found, actually it was during the falling of particles that maximum oxidation took place. So, the idea for a flash roaster came, that instead of bothering about passing the sulfides from one hearth to another, why not just drop from the top the concentrate and air, and you get at the bottom the calcine. It can be done. Then there is a sintering machine where also roasting takes place in a continuous manner. Then you have talked about smelting, blast furnace smelting, as is applied for iron making. This can be applied for lead. We have talked about reverberatory furnace, where reactions occur over a long time. We can produce matte, which is a mixture of sulfides and slags. Then we have talked about reactors where one combines roasting as well as smelting. So, initially we thought of flash roasting, now here is a flash smelter. After roasting, it goes smelted also, and again we can directly produce matte and slag. We have discussed this in more detail with reference to some oxidation reactions, the application of the Ellingham diagrams, and how we generate these stability diagrams. I would not go into all this. I have given an example of application of vacuum, when vacuum is required, and you can calculate what kind of vacuum we need for a reaction to happen, which normally will not happen. See, normally for reduction of this, free energy change is positive, but if we can remove this CO, application of a vacuum, then we find that equilibrium partial pressure is this. So, below that pressure of PCO, the reaction can be made possible. We have talked about thermit analysis, thermit reaction, analyze that. we have talked about a similar reaction which we will call now metallothermic reduction of calcium reducing TiO2, and then I mentioned that we can write a chemical reaction like this, but sometimes in metallurgical operation this will not be accepted, because calcium as a reducing agent would become gas at the temperatures where this should happen. So, it will require a bomb or a closed chamber. Titanium melts at 1670 degrees, calcium boils at 1492, calcium oxide will melt only at 2600 degrees. So, there is a mismatch of melting points and boiling points. This sort of thing will not form the basis of a metallurgical operation. We came to hydrometallurgically, saw the advantages, and I mentioned is ideally suited for lean and complex ores. There is greater control because things are happening at low temperatures, room temperatures very often, or slightly elevated temperatures, but it is easy to control because things are not happening far too rapidly. Environmental problems coming out of gaseous emissions are not there. We do not have to depend on coke as pyrometallurgical operations very often depend on. It is becoming a costly reducing agent. There is no question of CO2 emission. It does not mean all hydrometallurgical operations are very clean environmentally, because many of the operations also reject slimes, they reject effluents which are also not good for the environment. Metals can be produced in a variety of forms, not liquids of course, but the solids can be in crystalline form, in powdery form. Sometimes we can even produce particles of given shapes, as we do in the case of nickel, when you reduce nickel amine solutions by hydrogen. There are some basic disadvantages which I have already mentioned, that we are dealing with dilute solutions. We need lot of plumbing, pumping, there is tremendous amount of space is required, there are corrosion problems, reagent costs, equipment costs are high, effluents can create problems. Now, essentially in hydrometallurgy we need a concentrate which will be leached. During leaching, generally we take the metallic values in solution and the gangue is rejected in the solids, but opposite of that is also done. We saw in the case of monazite leaching by alkali in our country, alkalis dissolve away the undesirables, the desirable part remains in the insoluble residue. In the case of aluminum, alkali leaching takes the aluminum value into solution, the titanium ion that we do not want to come in the leach liquor is separated as a solid residue. So, leaching does not mean taking metallic value in the solution, it can take the metallic value preferentially in the residue also. So, the whole idea is the agent must be selective, leaching must be rapid, should allow high concentration for rapid action, the leaching reagent should not corrode equipment, it should be economical and should allow regeneration. Now, there are a whole range of things used in leaching. Sulfuric acid is very common and acids are stronger reagents, they dissolve things faster to a greater extent, but there is also danger of dissolving all kinds of things we do not want to dissolve. Whereas, alkalis are milder reagents, but they may be safer from the view of more impurities coming into solution. And there are also during leaching many reducing agents are used like MnO2, KMnO4, FeCl3 etc. will increase the oxidation potential. The various hydrometallurgical steps I gave a flow sheet, leaching, then purification etc., and then there are some other things that you can read up. I try to show how kinetics can be applied in analyzing leaching reactions. Like here is a solid mineral surface which is reacting with a leaching medium, and we see it as the reagent concentration from the bulk getting depleted when it comes to the surface. It is coming this way. Metallic values that dissolve at the surface diffuse out into the bulk, and when it diffuse out, there must be a concentration profile going down. The concentration must be increased here. If there are some other products, residues, apart from metallic volutes go into solutions, this would also have a concentration profile. If there is a solid porous residue, then the diffusion processes take place through that residue. Reagent has to the reagent has to come through the layer to the surface of the mineral, and the metal that is going into the solution has to diffuse through the porous residue, etc., etc. Suppose there is a leaching reaction where the intermediate residue layer is not porous, but is very adherent, then leaching reaction will stop. So, this possibility is also there. We discussed this little more from kinetic point of view, that any leaching reaction can be expedited by stirring, because there is a concentration profile at the surface and there is a concept of boundary layer, where say 99% of the concentration change takes place. So, if you stir the solution, the boundary profile is reduced, the concentration profile is made steeper, because the boundary layer becomes thinner and the stirring speed increases. But in this case, if you plot the stirring pace against rate, we find that beyond a certain stirring speed, the rate of diffusion cannot increase, because it has been reduced to the minimum, the boundary layer thickness. So, then only temperature will have to be increased. So, we have done this sort of analysis, and we have done this analysis particularly in case of cyanidation of gold. There is a surface where there are gold particles and cyanide ions are in the solution. Cyanide ions have to diffuse towards the surface. The oxygen has to diffuse to the surface, and gold cyanide that forms at the surface have to diffuse out. So, we did an analysis of that to know what will be important when. Is partial pressure of oxygen important, because that is also reactant? Is cyanide concentration important, because that is also there as a reactant? Then we analyze that under different conditions something is more important than the other. We talked about a cementation reaction, that iron filings put into copper sulphide would produce ferrous sulphate and copper will precipitate. It is an electrochemical reaction with a cathode area and an anode area. We made an analysis to understand what factors will govern the rate of the cementation process. It is not very difficult to understand. Then we have come to a very important area, and we looked at it from thermodynamic point of view, that zinc, when reacts with H2SO4, releases hydrogen, because zinc is more electropositive. We can write a general thing that a metal ion which is more electropositive dissociates hydrogen ions. Now, suppose we have in the solution nickel ions, cobalt ions, can we precipitate them out as a metal by hydrogen? Now, normally if the metal is not very reactive, obviously metal ion will not react, metal ion will not react to generate hydrogen. But if it is a reactive metal, then it to react to produce hydrogen. Then how will hydrogen precipitate from the solution a metal which is reactive. For that we have to do an analysis. We have written this reaction in the other way, that we intend to convert metal ions in solution into the metallic form by reaction with hydrogen. Now, normally, as I said, reactive metal ions cannot be converted to metal, because this reaction will predominate. But we can make this thermodynamically feasible by increasing the pressure of hydrogen, reducing hydrogen ion concentration, and try to see whether we can push it to the right. This will never be possible for say sodium or potassium or cesium and things like that, which are so reactive. It does not matter how much of hydrogen pressure you apply or how much you lower this down, which means how much acid you make, this will not take place. But there are cases which are marginal cases where this will happen, and this is the kind of analysis we have done. We have looked at, we have expressed this in terms of hydrogen ion potential, pH and pressure, and come up with an equation in terms of metal ion concentration, which is a function of electrode potential of metal, and one has to be more than the other, so that the reaction takes place. And then finally, we have got a plot which shows the variation of potential with metal ion concentration for various values of pH 2 and various values of pH. And we have shown that while normally say nickel ion will not be cannot give nickel metal, but if we go to a suitable pH value, or if you apply the suitable pH 2 value, the lines for hydrogen ion potential and metal ion potential in case of nickel and cobalt will cross. Something like zinc cannot be zinc metal cannot be produced, no matter what pressure of hydrogen you give or what is the value, no matter how alkaline it is, because it is far too above in the electrochemical series. So, this analysis we have done, we have shown the pH requirements for equilibrium pH values, and then we have shown that if you try to make something very alkaline, then also there is a danger of precipitating hydroxides. So, we said there has to be precaution taken, and one way would be to stabilize the metal ion as an amine, and we have discussed what is the optimum condition, say in the case of nickel, and discussed several other things. Then an interesting thing I have also said, that while nickel and cobalt can be precipitated from acid solutions with hydrogen ion pressure, hydrogen gas pressure under normal range, but adjusting the pH, the particles that come out can be of various shapes depending on some catalysts that we put in the system, and we have talked about some catalysts that give rise to particular shapes of nickel nuclei. For more details, you have to see the book. In module 4, we have talked about electrometallurgy and refining of metals. We have combined the two because electrometallurgy generally produces metals of very high purity. Generally, there are exceptions, and refining of metals also aims at producing high purity. So, electrometallurgy in a way is a step towards refining. That is why I have put them together. Secondly, electrometallurgy has come in the history of metallurgy much later than pyrometallurgy and hydrometallurgy, because electrometallurgy had to depend on invention of electricity. Otherwise, you would not have electrometallurgical process. We have given a classification of electrometallurgical processes. We have talked about structure of solvent media, aqueous solution, few salts where electrolysis takes place. Then we have gone into some very interesting discussion of molten salt systems and Temkin model. We have talked about principles of electrolysis and principles of electrorefining. Then we have talked about performance criteria of electrolytic cells. Here is a classification of electrometallurgical processes. Now, by the word electrometallurgy, many things are implied, but we have picked up from the entire gamut of things only this area, and that is neither this nor this nor that nor this. We have talked about electrowinning and electrorefining. Only these two we have talked about. We have not talked about many other things, because they are not directly related to electrolytic processes. Electrolysis, this is structure of water molecule. No, water is a polar molecule. So, we never have H2O. We have many H2O molecules associated because of this kind of bonding. That is how we get hydrated ions. As regards molten salt systems, they can be of many kinds, single component systems, multi-component systems, and etc., etc. You will find when we talk about fused salt electrolysis, very rarely we have a single component system. Always it is multi-component. There are very good reasons for that. First of all, when you mix 2-3 salts, your temperature, melting temperature comes down. So, you can carry out an electrolysis or electrorefining process at a lower temperature. There are also some other reasons. Try to remember that, or else I will remind you just now. I have given you some data to show what kind of purities are obtained. You see, during electrowinning from aqueous solutions, we get purities of 99, 99.9, 99.8. Very often we have to have such purities, because unless the solution is pure, you cannot do zinc electrolysis, because zinc is normally above hydrogen. It is only in a pure solution that you can have activation over potential, where the hydrogen potential exceeds that of zinc in the EMF series. So, we need extreme purification of the zinc leach liquor. Yet, the metal you produce really is not required at that purity for most applications. Most important application are galvanizing, which will do with a lower purity, but we can't help. We have to put pure zinc. In some cases like copper, we settle for a slightly lower thing, but it has to go for electrorefining later on, because we want to recover from the precious metals. We have also given some ideas about the kind of what kind of salt mixtures we take, what kind of current density we have, cell voltage, etc., etc., etc. We have given you some typical data for aqueous mode data for aqueous systems for electrorefining, which is one step beyond electrolysis, and that is to produce purer copper and get some byproducts out. I have talked about this over voltage phenomenon, which changes the voltage at the electrode, either because of a concentration over potential, because when the current flows, the bulk cations are flowing towards the cathode. The flow has to be because of a concentration gradient. This gradient becomes steeper when the current increases, because there is more flow of the cations, and which means you have a steeper gradient. That is why a greater flow, but there is a limit beyond which we cannot push it further, and that is becomes rate controlling. So, there is, because of this concentration gradient, a concentration over potential, and then a limiting current, or for a given area of the electrode, a limiting current density, which limits the amount of metal you can deposit on a cathode in a given cell. Because of concentration over potential, my analysis shows that the potential of the electrode does not change so much, but then it sets a limit to production. Now, in some cases the limiting step is not concentration over potential, but activation over potential, which makes it possible to have zinc in zinc electrolysis. But then this concept of limiting current density is very important. Why it is important? Because then in a given cell we are fixed. How do we increase the productivity? For that, couple of methods are available. We can rearrange the electrodes in various manners, or you can use a fluidized bed cathode, where the effective surface area of the cathode becomes much larger. I have shown a figure of that. Before that, I have given one or two solutions, one or two problems, simple problems, of one for fused salt electrolysis, one for aqueous electrolysis. I have given some data for electrowinning from molten salts. What kind of cell voltages in this case would be slightly higher, because you are dealing with more stable salts. At higher temperatures, your current efficiencies suffer, because other kinds of reaction can take place. Your energy efficiency would be lower. Many other data we have given, but you will see in all cases the supporting electrolyte which dissolve the solute is never a single salt. Mostly it is a salt mixture. Incidentally, the supporting electrolyte, the salt mixture, has to be more stable than the solute, otherwise something else will get electrolyzed from that supporting electrolyte. Then we have come to talk about the energy requirement, and we have seen that energy requirement in electrometallurgical processes will be more, in pyrometallurgical processes it will be low. We have also discussed the unit energies for production of primary, secondary metals, again to show how things are different when there is a electrometallurgical operation. Because of the use of electricity, your energy consumption is very high. Steel, lead, where your concentrates are of high grade, and the operation does not need too much of energy, your energy consumption is better. Then I discussed, just to show how things are analyzed, a very interesting reaction goes in the name of Van Arkel process, or we can also call it a vapor transport process, that we can take an impure metal, make it react with a gas phase to produce a second gas phase as one temperature, then decompose that gas phase at another temperature to produce pure metal. So, take impure metal, this should be plus, react with a gas phase, produce an intermediate gas, take it out, then sometimes at a higher temperature decompose to produce this, sometimes at a lower temperature it will produce a purer metal. And I have given an analysis as to how this is to be done and what are the factors that govern it, and take for particular reference we have taken reaction in case of tungsten, tantalum, hafnium. You form an intermediate chloride which will be decomposed to produce pure tungsten in another chamber. And we have shown that we have to understand the reaction in terms of enthalpy change, entropy change, and melting point. Then it came to some general conclusions that no transport of this kind is possible if the delta H value is 0, if the absolute temperature of delta H naught is very large, then too there can be no measurable transport, and it is delta H naught sign that depends the direction of vapor transport. Then there is also this element that delta S naught, if it is not equal to 0, is a delta H, some condition regarding entropy change also. This you have to cannot be done simply. I have also talked about purification using ion exchange resin and solvent extraction, how things are done. I will not go into those. Talked about different methods of refining, separation by liquefaction, and this there have been examples of that later on. If we have impurities like lead, if you consider lead zinc diagram, you see what happens when you go to higher temperatures. We can create two liquids, one very rich in zinc, one very rich in lead. So, if you have an alloy of this composition, if you go to that temperature, will produce a liquid lead percentage so much, zinc percentage so much, and their relative proportions will depend on the lever rule. So, this is one way from a alloy we can separate out the components simply by heating. Similar liquefaction, possibility of separation by liquefaction, another system. We can separate constituents from an alloy by differential distillation. Like if we have aluminum and magnesium, if we heat the alloy, magnesium will evaporate first, because this is the vapor pressure of magnesium. It reaches 1 atmosphere at low temperatures. Aluminum will volatilize at much higher temperatures. Okay. We have talked about vapor liquid equilibrium, we have talked about zone refining. I have talked about these things in a very cursory manner, because they are given in books, arc melting, electron beam melting, electrosag refining. These things one has to read up. Now, up to this we discussed the principles, then we came into the extraction processes for specific metals, and these were done in 3 different models: metals from oxide sources, metals from sulphide deposits, and metals from halides, not all naturally occurring halides, but naturally occurring halides, and also halides which were the starting point of some metals, and these halides may have to be prepared from oxide deposits. Talking about metals which come from oxides, and the learning objective was basic approaches in oxide reduction, special features of specific extraction processes, and extraction of metals such as magnesium, aluminum, tin. Ferroalloys also I included in this, because they also come from oxide sources, and I have given some discussion on energy and environment related issues, which have been discussed in more detail towards the end. Magnesium we have talked about its uses, and then we have seen that essentially the process depends on dolomite decomposed to produce Mg on CaO reduced by ferrosilicon or silicon. Magnesium comes out as a vapor, and the reaction is made possible by taking out the vapor continuously by a vacuum. That is why the reaction becomes possible, and this was first introduced during Second World War by Dr. Pigeon, and that is why it goes in the name of Pigeon's process. Reducing agent is ferrosilicon. We also produce a slag, but the trick is that the metal comes out as a vapor with a pressure at a pressure lower than 15 millimeter, and that is what makes the reactions possible. We have talked about the mechanism, how it takes place. You might think it is a reaction between a solid and a solid, which is not true, because solid-solid reactions cannot be very efficient. How often do solid particles come in contact with each other? The surface of contact is very small, but essentially it is a reaction of a solid with a liquid. Initially, the iron reduces CO to produce a liquid calcium, and it permeates the solid. A liquid calcium iron alloys permeates the solid briquettes, and that is where the reaction takes place. It is not a solid reaction. An advancement of this process is where we make everything molten by having a bath at 1500 degrees centigrade by addition of alumina to form a slag. It is called electrotherm process. Then we came to aluminum. There are many uses of aluminum, and today after steel, the most two important metals are aluminum and copper. Aluminum of course has good thermal conductivity and electrical resistivity. It comes fourth in the category. Silver, copper, gold are better than that. And the key to aluminum extraction is Bayes process, which produces pure alumina. It depends on many factors. Some of them have been considered: particle size, concentration of leach liquor. People have come out with an equation for the rate of leaching. Temperature should be high, but they make the temperature high, and sometimes it operates at 220 degrees leaching. You need lot of pressure in an autoclave. Some people would rather settle for lower temperatures, because autoclave operation at higher temperatures means more expensive equipment, more energy. So, the different companies have different ways of doing. No two companies act in the same manner. Eventually, everybody tries to produce pure Al2O3 from which will go into an aluminum cell. Now, what is the reaction? When alumina dissolves in cryolite, ideally we should try to get aluminum metal from aluminum ions and oxygen from Al2O3's oxygen part. Unfortunately, to take out oxygen as a gas, you need a platinum electrode. You can't think of platinum electrode for the surface. People are thinking of inert electrodes which will have TiO2 on the surface. It has not come in the industry yet. We use a consumable electrode which is graphite. The oxygen will go to the anode, which is graphite, and there it reacts to form CoCO2, which is good news as well as bad news. The good news is, because carbon is taking part in the reaction, taking away oxygen, it makes decomposition of Al2O3 easier, and decomposition voltage comes down. So, the energy requirement comes down as compared to if oxygen was released as oxygen. The bad news is, by consuming the oxygen, removing the oxygen which reacts with carbon, you generate CO and CO2. The proportion depending on the temperature operation. Because it is 1000 degrees, there is more of CO than CO2, which is something we do not want. Now, many people have thought what to do about it. Can we inject a reducing agent at the anode, say hydrogen or methane? We have given some analysis to show there may be marginal advantage, but there is no technology for doing such things. Ideally, we should go for an inert electrode where there will be no carbon consumed, no CoCO2, but then you have to have higher decomposition voltage, which means more energy, which means somewhere else you are producing, you are consuming more electricity. So, you have to balance this. The amount of CoCO2 you are saving here, is it more than amount of CoCO2 you are releasing at a power plant from which you are drawing power for electrolytic solution. I have given you a sketch of the aluminum electrolysis cell, aluminum anodes, and this is the cathode. this cathode eventually gets poisoned, and when this cathode is thrown out, nobody knows what to do with that waste cathode, because it is full of fluorides, and as of now it is only dumped. This electrode, carbon electrode, gets consumed. So, it has to be changed from time to time. A fresh one is brought and screwed on, or there are today Soderberg electrodes, where a carbon paste is continuously sent down through a pipe, and the paste gradually solidifies and is come to high temperatures, and it becomes the anode, but it is consumable. The trick here is we have aluminum at the bottom protected by the electrolyte, and there is a crust of L2O3. That is how the process occurs. There are equations as to what all things affect current efficiency. Then we have said it is not so simple an reaction during electrolysis, that L2O3 decomposes to aluminum and oxygen goes and reacts with the carbon anode. It is not so. All kinds of things take place. There are all kinds of anions existing there, and because of their existence there is evolution of fluorine gas, there is evolution of other gases that you do not want. Not only they cause contaminants in the environment, they also bring down the current efficiency through undesirable reactions. Now, lot of attempt has been made over the years to bring down the energy consumption, and the energy consumption has come down. It is difficult to go to the theoretical energy required for dissociation L2O3, because you need some energy to keep the bath in hot condition. The bath resistance gives heating. Therefore, you need in theory some energy to decompose L2O3, and then you need some extra energy for heating of the bath. And that is why it is coming down to the minimum, which must be above the theoretical minimum that comes from looking at the free energy of formation. Reduction in net carbon consumption with improvements in cell design. In cell design, the carbon consumption is also going down. That also would mean less generation of CO1, CO2. Here is another design of electrolytic cell, which I have shown in connection with some discussions. The cathode anode spacing, this spacing is very critical, 3 to 6 centimeter. The current range is critical. All these are very critical parameters. In reality, we have many cells in series. This is the look from the top, this is the plan view, this is another view of the cell to show that everything is enclosed, because you do not want the gases that come out just to go helter-skelter. They all have to be taken out very carefully through certain chambers. You see the carbon lining, molten aluminum, on top of that there is the electrolyte layer. I have given some equations to show that not only is aluminum and oxygen released, oxygen becoming CO2, there is also other species that come out, and that is why. Then there is a very interesting discussion I put in, a paper by a man from the industry, because I wanted to show you what that man finds important in the industry. There is a picture of the aluminum electrolytic cells in a long series. That is how an actual plant looks like. They have given some data, talks about what are the important issues, that there are actually plans to recycle 100% of aluminum by 2020. In that case, you do not have to produce aluminum through electrolysis. This may not be possible. It is not a very utopian thing, because aluminum does not get spoiled. So, when a consumer has used aluminum and discarded, it is not going to get corroded. So, it can be in theory recycled, but in countries like India, where we have not reached a certain level of development. We have to keep on producing more aluminum just to satisfy the needs of the classes who are coming up in development. So, we will not be able to recycle the entire aluminum by 2020. Advanced countries should do that. We need technologies to produce non-zero emission from cells. Electrical energy consumption has to be brought down. Then there are some other goals, mostly connected with energy consumption, current efficiency, gas emission, carbon consumption, and the industry is trying to improve on all counts. There was a list of R&D thrusts that I discussed, all related to what I just mentioned, and then discuss the very trick of operation in aluminum cells. There is a very small window. There is a working zone is very small. You cannot increase the bath resistance too much, you cannot decrease it too much. If you decrease the bath resistance too much by bringing the electrodes too close, then there will not be sufficient heating of the electrolyte. If you increase the resistance too much, you will get into a lot of problem, because you might get into operational difficulties. Similarly, alumina, you see the alumina versus cell resistance. If the alumina falls too far below a limit, you will have what we call anode effect. Some gases cover the anode and aluminum cannot be deposited. Then sparks go from one cathode to anode without causing electrolysis, it only causes heating. If the alumina concentration is too high, then it will exceed the solubility limit, it will precipitate out as a sludge. There are all kinds of problems. So, it has to be a very narrow window of 6 to 8% or something like that. Then the man from the industry has talked about market and demand pull, how the economy is growing, is likely to grow even faster in future. The aluminum demand we think can reach from present 0.7 million tons to 1.1 million next year, 1.7 million tons by 2015. I am sure Mr. Pugajendi has addressed these issues also. Then we have the smelter capacity of some kind. We might have bigger smelters, and we do not design our own smelters. We import designs from abroad, get consultants from abroad. We do not have engineers and metallurgists doing the job for us. So, a lot of money is going out of the country simply for this, and that is why he has listed some ironies, that even if India embarks today to create an Indian specific aluminum smelting technology, it may not be ready by 2015. We do not have our own technologies. All technologies are supplied by leading companies of abroad. Quality manpower is not available. Maybe some of you will go. Incidentally, until recently these companies never paid very well, but now things have changed. The young metallurgists who are joining these companies are being paid very heavily, and I have seen some very young bright boys and girls even willing to go to very remote areas where these alumina smelters are there, or leaching, the bare process plants are there, because the pay is good, the company treats them well. So, it is a very good option for you. But essentially the emphasis has to be creation of adequate quality manpower, and industry and national planners have to accept that there is something wrong with the present system of giving enough incentives, attracting young people to this industry. I have given in details something about Hindalco, the largest integrated aluminum plant, what they have, what they need. They have an aluminum refinery where power is coming through cogeneration. Cogeneration means simultaneous generation of electricity and steam. You need electricity, you also need steam, which will go for Bayes process. We need a caustic soda plant. you produce caustic soda which will go for leaching. In the smelter also you need power, you need aluminum fluoride, then fabrication rolling mills, all these things they have. You see how the smelting capacity is gradually increasing in our country. We have shown here which all companies are producing aluminum in India and what is their share: Sterlite, Nalco, Hindalco, Indal. This is their production share, this is their market share. Then I ended the discussion by talking about dimensions of future growth. Metal production has to go up, alumina production is going up, rolling capacity has to go up, and some other goals that we have. We gave a cost breakup. The most important thing is to show that according to the figures given, in aluminum production at Hindalco, power is 40% of the total cost, and that you see why aluminum is so very sensitive from the energy point of view. Then there was an analysis of energy consumption, what we can do to bring it down, but companies definitely are trying. That is why the energy consumption is slowly going down, mostly because of the average pot voltage is going down. There is a lot of computer control and other things to make the operations very smooth and standardize the quality of alumina, quality of bauxite, all the operating parameters. When things are very smooth and standardized and things are controlled, the process controlled by computers and automation, then you can minimize your energy consumption. And there was some data given as to what are the financial implications of slight reduction in voltage, and that is phenomenal. Over the long time, even small changes in power means a lot of advantage in financial terms. These are some data, pot line details. Then there were some challenges for the Indian aluminum industry listed. What are the goals? Reduction in consumption of energy and carbon, indigenous technologies, mathematical modeling, reduction in environmental impacts, increase in per capita consumption, recycling, etc., etc. All these can be done if bright young people come into the aluminum industry. I hope some of you will. Then I have given some discussions on ferroalloys, which I will not discuss now. I will end the discussions here today. Thank you. There are 4 more modules left, 6, 7, 8, 9. I will quickly review them in my last lecture. Thank you very much.